we were discussing the instruction set of a computer. We said that the instruction set is generally grouped into several classes. We discussed some of these classes like data transfer, then arithmetic operation, logic operations, etc. We were discussing the branch instructions and we came to the jump to subroutine or call instruction. But before we can discuss the call instruction in detail, let us discuss another group of instructions which we call the stack instructions. All of you have know what's a stack. It's a data structure in which items can be pushed on the top and can be removed, that means popped from the top only. You have written programs for that stack. Now the stack can be implemented by means of the hardware also, and it gives many advantages. We'll see one advantage almost in the next instruction. But first let's see what how the stack operates in the computer. Okay. Now say this is our memory. Increasing memory location. Now we can define a portion of the memory as a stack by defining the stack pointer. Okay, for example, say this is our stack pointer. Say this is the memory location 700. Okay. Now this is basically a hardware register. Say this contains 0700. Then the stack pointer, this hardware register, points to this memory location, and this is the present top of this stack. Okay. Now as the stack pointer grows or the stack pointer decreases, the top of the stack grows and it crashes. Right. For example, say suppose now this is the top of the stack and the content of the top of the stack is say 25. Right. Now there is an instruction which we call push instruction. Say if we say that push R1, then the content of R1 now will be pushed onto the stack. Okay. Say the content of R1 is 100. Right. What happens is the stack pointer will be automatically incremented fast. Say it will contain 0702. Okay, which means the next location of the stack cell. I'm assuming that each cell is taking 2 bytes. Okay, then it will be incremented to 0702 and 100 will be pushed into the stack. Okay. Now similarly, if we then say push R5 and the content of R5 is say 64, then the stack will be incremented, stack pointer will be incremented to 0704. Okay, now it will be it was pointing to here, it will now be pointing over to here, and 64 will be pushed here, the location being 0704. Therefore, every push instruction, what happens, the stack pointer is first incremented to point to the next memory location, and the operand is pushed as the top element of the stack. Similarly, the situation is that if we pop it out, that means if we say pop simply say X, then the top of the stack, which is 64 now, will be taken out of the stack and will be sent to the location X. That means X will now contain 64 and the stack pointer value will be now reduced by 2. It will now contain 0702. Therefore, similarly, if we pop once more, okay, the 100 will be taken out and the stack pointer will come back to 0700. Okay. Now, which means that every push first increments the stack pointer and then the operand is pushed into the stack as the top element of the stack. And every pop reduces the stack pointer, okay, but after the element of at the top of the stack is taken out, the stack pointer is reduced. Okay, therefore the pop is a complementary operation to push, and similarly push is a complementary operation to pop. Okay, now we can see that if we put, say, several operations like this, say push A, push B, push C, right? In that case, that A will be first pushed, then B is pushed, then C is pushed. Okay, the stack I am assuming that growing towards increasing memory location, and then I say that pop X, pop Y, and pop Z. Then C will be taken out first and goes to C. X, B will be taken out second and will go to Y, and A will be taken out third and go to Z. Therefore, popping will take place in the reverse order the pushing has taken place. Okay, naturally this is the property of the stack, and every time when the stack grows or the stack crashes, the stack pointer decreases, the stack pointer always points to the top of the stack. Okay, this is the property. Therefore, in the case of a push, the stack pointer is incremented first and then the element is placed. In the case of a pop, the element is taken out first from the top of the stack and then the stack pointer is decremented. Now, these are the two major operations so far as stack is concerned. And the initialization of the stack we can do, that means depending upon the initial value, which was 0700 here, the stack has been created from this point. The stack pointer, if we load with some other value, say 1500, in that case the stack will start growing from the location 1500. Okay, now with this, that stack of instructions discussed, let us come to the original discussion on jump to subroutine or call. Okay. Now the instruction can be either, sometimes it is called a call instruction or it is called a jump to subroutine instruction, JSR. Now let us see, say we are writing a high level program in, say, programming language C. Say we have written a main. Okay. Here we call some function, say f1 with its parameter. Say f1 is here. Okay, right? It has its own parameter and the function is defined. Somewhere we put a return statement. What we expect is that as the main is executing, okay, the control is coming sequentially or in a loop, whatever the program says. Ultimately, when it comes over to here, the control flows to this F1, then the function F1 is executed, okay, and on getting a return instruction, it comes back, the control comes back over to here. Now, this is at a high level programming language concept that we have. Now, let us see how this is done in the case in terms of machine instructions or assembly language instructions. Now, to understand this, let us recapitulate the simple program, okay, that we discussed earlier. Now, as I said earlier, that when the program starts executing, the program counter, okay, is initialized to, say, 0300, and now the program starts executing. The instruction is fetched and it is executed. The time that instruction is executed, the program counter is automatically incremented and it's now pointing to 0301, which is the address of the next instruction. Now this next instruction is now executed. The instruction is store accumulator X. Okay. Now the first instruction opcode is fetched, which is 04. As it is decoded, the program counter will be automatically incremented to the next value, which is 0302. Okay. Then the operand address is fetched from 0302 and then 0303. Okay. As each part is fetched, the program counter is incremented, and after the operand address has been fully fetched, the program counter will be pointing to 0304. Now that store accumulator instruction will be executed, and after execution the control unit will come back to the program counter, okay, and will get the instruction, get the address of the next instruction, which is in. The basic feature over here that I would like to emphasize is that as a program instruction is fetched, the operand is fetched and is executed, the program counter is automatically incremented as needed, and by the time that one instruction has been executed, it is pointing to the next instruction, so that after execution of the one instruction, the control unit takes the address of the next instruction from the program counter. Therefore, if we change the content of the program counter, the next instruction that will be executed is also changed to the address by which the program counter was loaded, and that way we can basically effect the branch instruction. Okay, and that way also the jump subroutine instruction is also can be implemented. Let us see the situation. Say the high level language program that we have already shown. Let's see how does it look like when we come to the assembly language. Okay, see, assembly language, that main program is here. Okay, the control flows is here. Then say somewhere jump to subroutine or call is there, and it's to F1. Okay, now F1 will start from some memory location. Let us assume that F1 starts from the memory location 0500. Okay. Also assume that jump to subroutine routine JSR F1 is in the location 0200, and it takes 3 bytes. Let us assume that the next instruction is say store accumulator X, and therefore the address of the next instruction, store accumulator X, will be 0203. Okay, and I said that this is a byte oriented machine, simple machine, and therefore these addresses can be any, either even or it can be odd. Okay. Now when this instruction JSR is being executed, okay, the program counter is now pointing to 0203, and at the end of this JSR instruction, the program counter will contain 0203. Okay, let us see that. Let this be our program counter. All right. It's now containing, when this is being executed, it's now containing 0203. Now what happens in the JSR instruction is that we have a stack somewhere in the memory. Okay. It grows downwards. We have a stack pointer, okay, and the content of the stack pointer is now pointing to the top of the stack, right? Let's say that this contains XXXS, right? Now, I'm assuming here that the stack pointer here is pointing to a cell which is 2 bytes consists of 2 bytes of memory. Therefore, when the stack pointer increases, it increases by 2 bytes, right? Now, JSR instruction when executed, what it does is that the content of the program counter is pushed into the stack by means of hardware. Okay, basically an hardware push is automatically generated by which that content of the program counter is stacked. That means now the content of the top of the stack is 0 to 03 and the stack pointer is now pointing to this top of the stack. And the program counter is now loaded with the address of F1 which is 0500. The program counter is now loaded with 0500 which is the address of the beginning of my function F1. Now JSR instruction is over. Next instruction naturally will be taken from the content of the program counter and therefore the execution of the program starts from this location now because program counter is containing 0500. Now this function F1 starts executing till it somewhere gets a return instruction. Okay, in assembly language we sometimes call it simply as a RET instruction. On getting a return, a pop operation hardware wise is executed and that pop operation is this, that 0 to 03 which was the top of the stack is taken out and is pushed into the program counter. Now you see as this function was getting executed, the program counter value was getting changed and somewhere it would have taken a value, say when this return instruction is executing say 0550. Okay. Now as the return instruction is executed, this stack top of the stack is popped out, which is 0203 is popped out and is pushed into the program counter, which means this is replaced by 0203 and the return instruction execution is over. As it is over, the control unit next takes the instruction address from the program counter which is 0203, which means that the control of execution of the program has come back to this point and the program execution starts from here. See, therefore, let's see what exactly is happening. On a JSR or a call instruction, okay, the control is transferred from this point to F1 here, okay, but before the control is transferred, the return address which is 0203 is stacked, okay. Now the control is in this function, the function is executed. On getting a return, that return address is popped out of the stack and pushed into the program counter so that the next instruction is taken from the address given by the program counter and the control comes back at this point. Okay. Therefore, basically jump to subroutine is a branch instruction where the return address is stacked and on getting a return instruction, that stacked return address is reloaded to the program counter to come back to the point from where the branch has taken place. Okay. Now you see this can be nested, can be executed in a nested form and repeatedly. For example, say you have a program here, so you have a main function here, okay, main, then a function F1, then a function F2, okay, and then a function say F3. Every1 has a return statement, this has a return statement, and this has a return statement, okay. And here we make a JSR to F1, okay, or say call to F1, right. What happens is this, the control is coming like this, at F1 the return address is stacked, so return address say is alpha 1, therefore alpha 1 is stacked. It goes over to here, right? Here, let's see, we have an instruction, say call F2. Here we have an instruction call, say F3, and there's no call over here. Then the control comes to this, say the return address, when it calls, control comes to F2, so return address is alpha 2, then this alpha 2 is stacked, okay. Then the control comes from here to F2, it comes down this, so return address is alpha 3, that is stacked, okay, and the control flows over to here, okay. Now F3 is executed, returned. Returned means it returns, it pops alpha 3, put in the program counter, and therefore it returns to alpha 3. The rest of the portion is executed, gets a return, alpha 2 is popped out, and you have control back to alpha 2, okay. Then the rest of the F1 is executed, right. On return, alpha 1 is popped out and pushed into program counter, and therefore we come back to this point and then starts executing from here. This is essentially that nesting of calls to functions, right. Now let's see what happens when the same call, the function is called once more, say as F1, right. Here the return address, say, is alpha 4, then alpha 4 will be stacked here when this call takes place, and the control goes here. Then the comes to this, alpha 2 will be stacked, goes here, right. Then alpha, call F3, alpha 3 will be stacked, return address, goes over to here, this is executed, comes back to alpha 3 by popping the return address, then the rest part is executed, comes back to alpha 2 by popping alpha 2, the rest part is executed, okay, and comes back to alpha 4, that means it comes back over to here. That means when I was calling from here, since the return address was alpha 1, I was coming back to alpha 1. When I'm calling from same function from here, since now the return address is alpha 4, I come back to alpha 4 and my controls of the program, okay, starts from here once more. This way you see that by means of stacking the return address and while returning, popping the return address, okay, we can implement that nested calls of functions very easily and efficiently, okay. This is a very good use of a stack. We'll find many other good uses of a stack when we proceed further. Now this more or less completes the different instruction groups that generally are there in a computer. There may be many more instructions of different types depending upon that how powerful and how complex the hardware is, okay. But for our purpose, this set of instruction is sufficient for our discussion. Now as we said earlier, that an instruction consists of two parts, okay. One is that opcode, which means that what operations can be performed. Another is that address of the operands, okay, we call that the operand part, right. Now the operand can be addressed in many ways, and different ways of addressing we call that addressing modes, okay. Let us see now the different addressing modes by which operands can be addressed. Now addressing modes, okay. Let us take some simple examples, okay, and tell the different addressing modes. First addressing modes that comes to us is register addressing. As we know that the CPU contains many registers, okay, and the more powerful the CPU is sometimes, okay, the more registers are there. The advantage of having registers within the CPU is this, that if you have to get an operand and if you have more registers, then you can keep the operands in the registers and you can get the operands from the registers almost instantly, very fast. But if it's not in the register, in that case you will have to go to the memory, fetch the operand from the memory, which takes some time, and therefore the execution of the program gets delayed. Okay, it takes longer time. Now, register addressing uh, register addressing concerns the addressing of the many registers that are there in the CPU. Let us take an example. Say data movement instruction, say move. Okay, it can be like this, say move R1 to R2. I am assuming that is a two operand instruction. This means that content of register R1 is to be moved to register R2. Here register is the address of the operand. Okay. Let's see, we'll talk about a concept which we call that effective address. Okay. Or EA. EA means that effective address is the address of operand after the addressing mode has been applied. For example, here this is our address of source, this is our address of destination. Okay. Register addressing means the register is the address of the source. Here the register also is the address of the destination, and therefore the effective address is the register R1 for source and the register R2 for destination. Right. Now similarly, say we can have another instruction like say add R4, R5 to R4. Okay, this is the source and this is the destination. It means the content of R5. Okay, this means that content of R5, okay, is added to the content of R4 and the result goes as the content of R4. Okay, this is the source, this is the destination. Effective address is R5 and R4, and the content of that address will designate by means of a bracket. Okay. For example, if M is a memory location, okay, then effective address is M, and then the content of M will designate by means of bracketed M. Now this is basically your register addressing, where the operand is in the register. Okay. Now, so let's come to another addressing mode, which we call direct addressing. Here, the address in the memory of the operand is given. Say, for example, we can have an example. Once more I am giving, almost all the examples I will be giving assuming that it's a two address machine. Okay. For example, say if I say add R2 M1, this M1 is the direct addressing. That means it is giving the location of the memory, okay, where the content of which is operand. Okay. Therefore, the effective address of the source is the location of M1. Effective address of the destination is register R2. Okay. It means that the content of M1, this instruction, will be added with the content of R2 and the result will be content of R2. Okay. Here the source is a direct addressing and the destination is a register addressing. Similarly, we can have say move M1 to M2. Both are direct addressing. That means content of M1 is moved as into content of M2. Okay. This is our direct addressing. Let's see immediate addressing. In the immediate addressing, one of the operand is kept in the instruction itself. Let's take an example. Say if we add R2 with 100. But 100 is the operand, it's not an operand address. And to say that it is an operand, we generally put the number sign here. Okay. Now, this means that 100 will be added to content of R2, and this comes as content of R2. Okay. 100 being a part of the instruction itself. Let's come to now the fourth addressing mode, indirect addressing. That indirect addressing is that you get the address of the operand from the content of another memory location. Okay. Take an example. Say we say add say register 9, where M1 is the address of a location, and we take the address of the operand, final operand, from the address from the content of M1. Okay. So let's take an example. Say this is M1 and say this contain 1000, then operand is in this location 1000. M1 is pointing to this, and we take the operand say 50 from here, which will be loaded into R9. Therefore, effective address is content of M1 for the source and R9 for the destination, and the operation is that you take content of R9, you take the content of M1, add, and that comes as the content of R9. Here the operand is the content of M1, and effective address is content of M1. Let's take another example. Say if we say that move M1 to say M2, this means that effective address of the source is content of M1, effective address of destination is content of M2, and the operation is content of M1 is moved as content of M2. Okay. This is our indirect addressing. Many times it is useful. Let's come to another addressing mode, which we call register indirect addressing mode. Let us take an example. Say move R5 R2. Here the source is in register indirect addressing mode. Instead of the register R2 being the effective address, its content is the effective address, okay, which means the content of R2 is not the operand, content of R2 is the operand. Just to give an example, let us see, let's say this R2 contains say 600, okay, then this 600 is not the operand, 600 now points to, R2 now points to the memory location 600. Whatever is contained in that memory location, say 190, this is the operand, okay. Therefore, effective address of source is the content of R2. Now, effective address of the destination here is R5. Therefore, this move statement moves 190 into R5. Okay. Therefore, the operation can be thought of like this. Say, content of R2 is moved as content of R5. Now, you see, basically this is indirect addressing, as has been told. We have given a indirect addressing mode example earlier. Now, these are useful in many ways. Okay. For example, all of us possibly remember that in the case of the high level language C, we can have a statement like this, okay, that P is equal to say address of A, then the memory location pointed to by P, its content, say we transfer to B. Such case, we can either use, say, register indirect addressing or indirect addressing that have been already discussed. Okay. Now, another advantage of this indirect addressing is this, that say one wants to access the data sequentially starting from certain location, or wants to scan the data, okay, say at intervals, right? In that case, what can be done is that R2 is first loaded with the initial value of the memory location from where the content should be taken, and then you can continue increasing the content of R2, okay, incrementing it, so that now it points, next time it points here, then it next time it points to the next location, and so on. Therefore, by just increment the value of the content of R2, say first time it is say 600, then say we increment by 2 to come to the next location, say 602, okay, then we come to the next location, say 604, and so on. Therefore, in a sequential order or in an orderly fashion, if we want to access the content of memory location, then the register indirect addressing turns out to be very useful. Now, there are certain enhancement or modification to this register indirect addressing, which also turns out to be very helpful. We will discuss it in the next class.